Welcome back. We're going to go ahead and get started with the last technical session of the day, followed by the spotlight session before we adjourn. Thank you for sticking around. Our next faculty presenter is Cecilia Huertas-Cerdeira. She's an assistant professor in mechanical engineering. Cecilia, the floor is yours.
All right, thank you. Thank you for having me here at the symposium today. So as Yancy mentioned, I'm an assistant professor in mechanical engineering, and my research is more on the mechanics side, so it's a lot less algorithms, but hopefully still interesting to the audience here, and maybe you can think about how to apply your algorithms to my system here. But today I'm going to be presenting about a new propulsion system that we developed for underwater vehicles. And so I'll start with explaining why we care about underwater vehicles and specifically the propeller that we're trying to develop. And so autonomous underwater vehicles have a lot of different applications. So we go from military applications. So this drone here, for example, is used by the Navy to hunt for mines. We also have scientific type applications. So for example, this is a NOAA underwater vehicle for fishery service. And we have more industrial applications. So this is a seafloor survey, for example, or used for seafloor service for oil rig installations. And we've seen in presentations today other applications, for example, farming of oysters also uses this type of vehicles. And so the autonomous underwater vehicles require sort of very precise characteristics. So they need to be very maneuverable. They need to be very efficient because they need to have long ranges. They need to travel far. It's very hard to put that vehicle in the ocean. And so if we need to recover it every very short range of time, we're not going to be able to take on the measurements that we want. And they also need to have reduced noise emissions, for example, for this application here, where we don't want to scare the fish that we're trying to research. And so one of the avenues that researchers have followed is to use biological swimmers as inspiration. The reason why is because fish and any other biological swimmer is actually a lot more efficient, a lot more maneuverable than anything that we can build up to date by engineering methods. And so the propeller that I'll be proposing here is a bio-inspired design. All right, the specific problem that we're trying to solve here is an application that requires both maneuverability and long-range propulsive efficiency. So for example, an application would be the monitoring of ice shelves. So we need our underwater vehicle to reach far distances all the way down there at the bottom of the ice shelf. So we need it to be very efficient, but we also need it to be very maneuverable because we needed to keep its own station. So if we slightly perturb the underwater vehicle, we needed to be able to move back to the same position. And so existing underwater vehicles and biological swimmers both have a trade-off between these two characteristics. So for an engineered system like this one here, that's very efficient. We have a very rigid, streamlined body. We have very few sort of additional surfaces. We only have one propeller that makes or reduces the drag on the system to make it very efficient. If we want something very maneuverable, we need all these additional thrusters that are pointing sideways. We need additional surfaces. And so the system will not be very efficient because it's generating drag. For biological systems, the most efficient swimmers are tuniform swimmers, which is this tuna type fish that is very rigid, has a large aspect ratio fin, and has this sort of lunate shape here, generates forces by a lift mechanism. If we want something very maneuverable, we have to go to sort of your reef type fish or fish that are very flexible or generate propulsion by systems that are not flapping, but something like this squid here. All right, and so the objective for our research is to generate an AOV that is both efficient and maneuverable at the same time. And so we know that the concepts that we have developed up to date can't really have these two characteristics. Biological swimmers don't have these two characteristics. And so what we'll try to do is merge both things and make a new type of system that can actually have both efficiency and maneuverability. All right, so this is the design for the autonomous underwater vehicle that we came up with. We're combining both biological and engineering traits. What we have is a very rigid streamlined body. And the important part here is this caudal fin propeller. So it's a propeller that it's at its rear end. We have a 3 degree of freedom spherical parallel manipulator that can generate very complicated motions of this fin. And so we can generate propulsion by flapping the fin, we can generate continuous rotation of the fin. And we're hoping to add maneuverability by adding these complicated 3 degree of freedom motions into our design. All right, and what I'll be talking here today is this maneuvering part of our underwater. Now we have this system that is a combination of both biological engineering systems, but we don't know what trajectory of all the very complicated trajectories that our fin can perform. The fin should follow to generate maneuvering forces. We can't really imitate nature because nature doesn't have this type of mechanism, and it's not something we've studied before in engineering. And so we need to figure out what trajectory to follow to generate maneuver. All right. This here is a back view of our system. So you're looking at the fish from behind, and we'll sort of parameterize the trajectory by 10 different parameters. We will draw this sort of trajectory of the certain center point of the fin, and this here is the position of this edge of the fin here. And so we have different figure 8 and ellipse type trajectories. We have varying stroke angles, amplitude deviation angles. We have different rotations, different phases, and so on. And so if we determine a range of parameters that we want to study, determine specific intervals for these parameters, we have something like 10 to the 8 combination of parameters. We can really test all of the trajectories that we have or that we are able to generate with this propeller. And so what we do is use data-driven methods to determine the best trajectory. All right, the specific method that we use is an experimental trajectory optimization. And so what we're doing is we're running an optimization algorithm in our computer. In this case, it's an evolutionary strategy. At each step in the optimization, we need to evaluate for a loss function. And so what we do is we evaluate that loss function experimentally. And so the experiments and the algorithm are all automated together such that this mechanism runs continuously on its own without us needing to manually perform this experiment. And so once we continue doing this loop, for this specific case, the optimization converged in about 700 experiments, which takes about a week to converge. Obviously, if we had to do this manually, we probably would take months to finish. All right. What are we trying to optimize for? In this case, we're trying to maneuver. And so we target a side force. So if this is our vehicle here, the force will be coming out of the plane, and that will generate a turn of the vehicle. We have a force ratio, which is the difference between the measured force and the target force that we're trying to achieve. And I didn't mention the experimental setup here. We have the fin, and we have our force sensor all the way up here at the center of rotation of the system. And so we can measure all the forces that we're generating throughout the trajectory. And then the efficiency here is a geometric efficiency. Essentially, it's measuring how much of the forces that we're generating in the direction that we want to generate them. So we're trying to generate this side force without generating any forward motion. And so the higher the efficiency, the less forward motion we'll have when we're generating a side force. So we define this loss function that is a combination of these two parameters. Right? If we run the optimization, this is the optimal trajectory that we get. These are sort of an experimental video with air bubbles in our oil to visualize the flow. But what we see is this very complicated trajectory that's not really very intuitive. And we're generating force. This is looking at the system from behind in this fx prime direction to the side. All right, the first thing we need to understand about this trajectory is that it's generating forces by rotation around the center axis. And this is not a rotation that biological systems can do. So fish usually just flap side to side. They do this sweeping motion. And that's why this trajectory seems sort of not very intuitive. It's because we don't really see it anywhere else. And so I'll go a bit through the mechanisms that make this trajectory efficient and how this trajectory works. So hopefully I can give you a better idea of why this 3 degree of freedom mechanism works a lot better than just having a regular side to side. All right, so to generate this side force, and again, in the fx prime direction, the strategy that this optimal trajectory follows has 4 different steps. The first one is a drag-based power stroke. So essentially, we're following almost a paddling motion. I didn't represent the velocities here, but the velocities sort of match the peak in normal force. And so for us fluid mechanicians, that means that this is a drag-based sort of power stroke. All right. After this first power stroke, the fin needs to reach another location so it can continue flapping. And it's trying in this second trajectory to minimize the amount of forces that it's generating. So the idea here is if you can't generate beneficial forces, at least try to minimize the amount of detrimental forces that you're generating. And so what it does is it just moves tangentially to its trajectory so that it's very streamlined and it's not generating very large forces. Right. This third stroke here is also a power stroke. In this case, it's a lift mechanism. And then the fourth stroke here is a return to position. So we have a bit of a negative force here, but it's still sort of a very efficient way of doing this. And one thing that I want to mention here is if we just rotated this fin around its central axis, it wouldn't generate any forces. And so we need to change the center of rotation of our fin to one of the edges. And so the way that this trajectory is doing this is by combining that rotation with the specific motion, this ellipse of the center point, such that the center of rotation of the fin is actually rotated or located at one of the edges of the fin, not where it's attached to the main system. All right. These are sort of the basic mechanics of how this trajectory works. There are a few unsteady mechanisms that make this trajectory very efficient compared to sort of similar trajectories. So what if you had 3 degrees extra sweep, or you had a couple degrees extra deviation angle? Why are those not the most efficient trajectories? And the reason is because it takes advantage of these unsteady mechanisms that I'm explaining here. So what we're seeing here is a delayed shedding of the start vortex. So if we have a paddling motion, your typical paddling generates a start vortex, which is this red vortex here. For those of you who are not familiar with fluid mechanics, a start vortex or a vortex in general is a low pressure region, and so it generates suction. And so having this vortex here generates a force on the fin in that direction. And so what this fin is doing is, in a regular paddling motion, the vortex is shed behind the fin once the fin stops. And so that generates a very high negative force, which is not what we want. And so what the fin is doing in this trajectory here, and the starting vortex you can see here rolls over the top of the fin to be shed instead of at the bottom here, all the way at the top, such that it's generating suction. And that's generated by that downwards motion of the fin down there. All right, another mechanism, and I'll speed up a little bit here since we're running out of time, is the wake capture that we see in steps 3, 4, and 1. So when we go up, we're moving fluid upwards. And then when we move back, we're again facing that fluid that is still moving upwards. And so that generates a relative velocity that is higher with respect to what we would see if the fluid wasn't in motion. And so it generates a larger force than it would otherwise generate. All right, and the last part here is, I mentioned before, the trajectory is combining that rotation around its center axis with the 3-dimensional motion of the center of rotation to generate this very efficient trajectory. What happens, and this is sort of to demonstrate that concept, if we constrain the trajectory of that center point to a line instead of a 2 degree of freedom trajectory. And so what we see is we get this other trajectory here, which can achieve that force of 17 millinewtons that we targeted, but the efficiency goes down very significantly. And so we need all these 3 degrees of freedom to be able to generate this maneuvering efficiently. Right. I'll skip through the effect of flexibility. I'll leave that for another time, but I'll summarize sort of the conclusions of this research. We designed an underwater vehicle that is both efficient and maneuverable, and it consists of a very rigid streamlined body and then a 3 degree of freedom propeller at its rear end. We developed an experimental setup that allowed us to optimize the trajectory of this 3 degree of freedom mechanism to be able to maneuver the vehicle, because it's not a trajectory that we can take inspiration from nature, for example, to maneuver our vehicle. And then the optimal trajectory that we obtained uses very large rotations around its axis. It uses this complex 4-step strategy to be able to maneuver, and takes advantage of these unsteady fluid mechanics in order to do that very efficiently. And so the last thing I showed is that the 3-dimensionality, which is sort of the novelty of this mechanism, is actually very important in this maneuvering strategy. All right, with that, I'll finish up. If anyone has any questions, I would be happy to answer. Yes. Yeah, so you should be able, the problem with optimization is that the optimization algorithm itself tells you what is the next point that you need to evaluate. And so it might not fall on the same points that you already have. You could try to sort of map and see if that sort of matches. And you could try to use that data to do some sort of machine learning type algorithm to sort of extrapolate those data points to something for every single trajectory that you have. So you can definitely reuse that data. Optimization on it would be hard to do, but you can definitely use it for something else.
Last video that you were showing inside the water.
Yeah.
Yes.
There you go.
So, would compute that flow analysis?
Yeah, so you could definitely do it computationally. These would be very expensive simulations to do. So this is sort of high Reynolds number flow. It's very complicated three-dimensional motion. So it actually takes a very long time to converge to solve for that fluid mechanics, which is why we do it experimentally in this case.
The computer vision lab will specialize on such problems.
So you would need a good sort of reduced order model for the system, which is hard to get in fluid mechanics in general, especially if it's this three-dimensional. But it's definitely something that you can explore. And there's people dedicated specifically to developing reduced order models of this sort of thing.
Scientifically, the question is, we decided that fish-like propulsion is more efficient than rotary propeller type propulsion. That that's the reason that you're doing. Is that correct?
Yeah, so it's sort of tricky. Fish themselves are a lot more efficient than rotary propellers. So rotary propellers would be something like 70-something% or 0.7 efficiency. Fish would be 0.9. They're very high. The bio-inspired fish vehicles that we can build are not as efficient as actual fish. So it's up there, but at least we know rotary propellers, we won't be able to improve the efficiency as much because they've already been sort of optimized for decades. So we know they're not going to go much higher, but we know that fish type propellers can go all the way up to where real fish are. And so that's the idea.
Thank you, Cecilia.
Yeah, thank you.